Okay, so this is the discussion for November 13th. We're going to cover two papers today, both discussing finding life essentially out in somewhere else, not other than Earth. So the first paper I'm going to cover is actually a pretty recent publication. You may have heard about it in the news. It was a big deal about phosphine gas being discovered in the Venus upper clouds. This is exciting because, of course, we're always looking for new ways to find life elsewhere, but it's a more conclusive possibility of life. So prior to this paper being mentioned in the media and reading it, of course, I had never even heard of phosphine. I've heard of phosphorus and things like that, but phosphine, or it goes by the chemical name pH3, and it's a colorless, flammable, toxic gas. And here on Earth, it's either made industrially or by microbes that survive without oxygen. So that's why it's a good indicator for possibility of life elsewhere, is because you have to either make it yourself or some little critter has to make it. So that's why they're excited about Venus, because we always thought Venus was kind of like this desolate hellscape because it's so hot and there's a lot of pressure and it's just, acid rain, and it's just a miserable place to be. So scientists have speculated before that microbial life could be found in the upper atmosphere of Venus, because this way they'd be away from the intense heat and pressure of the surface. The original thought was that phosphorus in the hyperacidic clouds would be oxidized. So to detect the phosphine single line millimeter wave band spectral detections, that is a mouthful, were conducted using two different types of telescopes, the JCMT and the ALMA. They use this type of consideration based off of previous work. So there is not a known abiotic source of phosphine on Venus, so we know there's not somebody on the surface producing it industrially. So this is an extensive paper. When I printed it out, it's like 43 pages. So I'm going to do my best to summarize it. But it is ultimately speculative. So it's a technical paper, and it presents the data and things like that, but it's ultimately speculative because it's not 100% conclusive yet. We need more studies. We need some in situ resources to go out there and actually collect some of this upper cloud deck to see what's in it. But just from what we can tell here on Earth, I will say it does look promising. So, of course, people got interested in this paper because finding life elsewhere in the solar system especially is always enticing. Nobody wants to feel like they're completely alone out here in the galaxy. And of course, astrobiology is a big hot topic now. So when this may hit the news, even I was kind of shocked. It was on like CNN and CBS and stuff. So, average people who don't partake in science every day were getting to hear about this. And even since the publication, though, I will point out some dissenters have come forward and been like, well, no, that's not true, or this is how we analyze the data, or something like that. I'm not going to really talk about those papers, but they do exist. You can go look them up. And it will be interesting to see whether data is produced on this topic. So I can read my notes. Ugh. The ultimate answer of what source produced the phosphine to detectable levels, which is about 20 parts per billion, will come from further data collection, like I mentioned before, hopefully in the form of testing the biosphere. Possible sources of the phosphine on Venus could be geochemical, photochemical, or biological. And again, this paper doesn't answer which one it was. It just says this is what we found. So we don't know the origin right now. They're like, yay, hopefully it's biological, but it could be geochemical and photochemical, but they don't know the exact methods of how those would come about. So Earth does have phosphine in its atmosphere, and it does come from biologic origins. pH3 is also produced in other solar system bodies, including in the reducing environment of gas giants, such as Saturn. And the method of millimeter wave band detection of the phosphine is actually used to find this compound in Saturn's atmosphere previously. So that's how they knew it worked to find this particular gas. Observations were first conducted across 5 mornings in June of 2017 at the JCMT. And absorption lines came from the cloud decks all over the planet, so they didn't just focus on one area, they focused on the entire planet, which is probably wise. So one fallback to this method is that it created high frequency ripples, so data reduction had to be used to reduce some of these aberrations. Figure 1, that's this one right here. It shows the data collected from this initial method, and it does allow for the small possibility that the readings are another molecule which has a similar wavelength. To determine the difference, they went to another telescope and used ALMA. It's a type of array, and they did this in March 2019. This array has better resolution, which allows for more details of the atmosphere to be determined. To test the second method, they used it to detect known molecules in the atmosphere and then confirm those wavelengths. So it's basically kind of like they calibrated it ahead of time by saying, is this actually what we're supposed to get if we know the wavelength of this molecule and we can detect it? So that way they know their data is not just completely weird. So figure 2 shows the data collected from ALMA, and there are some definite similarities in the spectral shape to figure 1. The right figure in figure 2 breaks down the data by region of the planet. So the top line is the polar region. The middle line is mid-latitude. You can see that's where the very similar portion lies. And the last line is the equatorial point. So based on my very limited knowledge of how this data works, the information on figure 1 and figure 2, part A, and the mid-latitude information all seem to be saying this, there is phosphine in the upper clouds of Venus around the mid-latitude region. So figure 3, scoot, there we go. Figure 3 shows an overlay of both sets of data, so you can see the similarities and the differences for direct comparison. This is the whole planet spectra, not region specific. I don't think they did region specific on the first test. I think they did that with ALMA because it had that capability. They also compared the data to what would happen if another gas was absorbed at similar wavelengths, the most likely candidate being SO2. No significant absorption was detected. And they're kind of scooting in. The right part of figure 4 compares the two absorptions. So this is the original, and then you can see the SO2 here. And you can see how different they are. This made the researchers conclude that the data does reflect the presence of phosphine. The paper then details how the data was reduced, compared, and checked for abundance. That gets into some stuff that is not my forte. So I'm gonna be like, I don't know how to explain that, and I'm sorry. So they do conclude that there must be an atmospheric surface or subsurface source of phosphorus, or possibly even delivery from space, to account for the phosphine that they detected. And another key thing to understand is how long does phosphine last on Venus, so they can further determine its origins. Lifetime of phosphine is based upon altitude and thermal decomposition. So that is something they are still working on determining, but that could really help us pinpoint where it came from, because if it doesn't last as long, but it still reappears, it might be biological in origin. So while photochemistry is an option for an origin source of phosphine, that process is not fully understood of how it works on Venus. So that's another thing they need to understand more. So this paper basically opens up a lot of doors. We don't know this, and this, but that's kind of how science works. And the authors stress the detection of phosphine does not automatically mean there's life on Venus. Venus, of course, does have many other obstacles that life would have to overcome to survive while living on that planet, because, again, like I mentioned, it's kind of a hellscape. But it is a promising step in the right direction, though. So for this paper, what do you guys think of these data points? Like, do you think it's realistic? Is it just a bunch of squiggly lines? What do you think the detection for life on Venus could mean for us here on Earth? Like, should we even go test it, or would it be too much of a negative consequence for that? You know, there's always the worry of contamination from our own spacecraft. And if we send a spacecraft into the upper clouds of Venus and we already have something on our own spacecraft that could be transferred to those clouds, like, how do we determine the, you know, good versus evil? Is it a necessary evil? Because like mold spores and things like that, you just cannot eliminate them 100%. So that's something to take into consideration if we decide to go test the clouds. So I'd be interested to hear y'all's thoughts. And today I will be on Slack during class. I can't actually be in class live because I'm now teaching full time. But I can be on Slack while I'm doing my distance learning for my students, so I can answer questions or talk to you guys in that way as well. And then we're going to switch to the other paper real quick. This one's by Casting, and it is about how do we determine exactly what makes a habitable zone, and where are the boundaries so that we can, you know, point our telescopes and things in those general directions around stars and determine if we could possibly find life out there. Because this is more about exoplanets. The previous paper was about our own solar system. This one's more outside of our solar system. So it's another technical paper that reviews the search for life elsewhere in the galaxy. Stars are characterized by their spectral characteristics. See if I pulled up this. So this is a comet chart you'll see, so you can see. I think we're a G-type star here in the sun, so this paper is focusing on these type of stars. So a little bit lesser than our stars in terms of temperature and luminosity. So they tend to kind of follow these based off sizes and temperatures and therefore luminosity. The bigger and hotter a star is, the shorter their lifetime, thus reducing the chances of finding a habitable planet anywhere near them. Because the biggest and brightest stars live fast and die young. So, like, you're really not going to find something near a hypergiant because that thing's going to explode eventually and take out anything near it. And that's not good for life, because we all know life takes a very long time to get from, you know, tiny microbes to us talking about this paper about tiny microbes being elsewhere. So if your star goes supernova, your life has no chance of getting anywhere near that unless it evolves at a totally different unprecedented rate, which I'm not going to get into. Our current definition of a habitable zone is the area around a star in which a rocky planet, so we're talking about terrestrial planets, not gas giants, can maintain liquid water on its surface. As we all know, our definition of life is very critical. We must have water. We're very sensitive creatures. Excuse you. That was my dog, sorry. So exoplanets may hold life, but confirming such a presence from Earth is obviously difficult because we don't have the technology to just zoom on out there and go collect some clouds and test them and all that. So we can't do in situ resources to test exoplanets. We have to use telescope data, and that comes with its own set of obstacles. So remote detection is how we accomplish all this. It's just a fancy way of saying telescopes. And I like that they point out that the biologists and the astronomers have different definitions of life. And they said the biologist's definition is not useful to an astronomer. And I kind of found that funny because I'm in both fields. So I am the bridge between the worlds. I find it funny. So astronomers have been attempting to determine what criteria they can use to determine, life or not. And an original idea was to look for extreme thermodynamic equilibrium, but that idea has been criticized. And then an idea came forward to search for the simultaneous presence of oxygen and a reduced gas that is produced by life, such as CH4, methane, or N2O. I think it's a nitrogen compound, and I don't remember the name because it's 5 in the morning. Exoplanets have been discovered using radial velocity. The transit technique is just where you point a telescope at a star and you wait to see if it dims and then goes back to normal. Like there's a planet passing in front of it. And through using the Kepler telescope. So they're also building the James Webb telescope, which is this absolutely massive telescope. And they're going to launch it soon, and I'm really excited about it. But once that's functional, it is hoped even more exoplanets will be discovered. I think Kepler, it said, discovered like 3,000 or something like that. So James Webb is even more powerful. It could probably discover multitudes of that. And hopefully have actual more data on them too. As opposed to, yeah, there's a planet, but we don't know anything about it. So it should also be noted that anaerobic life would produce different gases in an atmosphere. So excluding those planets based entirely off their atmospheres could do more harm than good. I'm still going off the assumption here that microbial life is going to be the most common that we're going to search for, because I'm not expecting little green men, but microbial life seems pretty common and resilient. So in situ testing of planetary bodies proposed to have subsurface liquid water is possible for closer objects, such as Europa. So Europa is not really in our quote-unquote habitable zone in our solar system, but we do think it has subsurface water, so that's why we want to go test it and see what's going on. But the determination of water presence and any microbial life within is not really possible right now for distant objects. Even getting to Europa's a challenge, and that's kind of one of our neighbors. So any planet outside of our solar system is really hard to test. So planets on an inner edge range of the habitable zone can lose their surface water if a runaway greenhouse situation occurs, like what happened on Venus, or if the temperature exceeds 340 Kelvin. Which causes much of the water to become part of the upper atmosphere, where it can have the hydrogen escape to space. So space steals and giveth both. So habitable zone boundaries are based on stellar flux at the top of a planet's atmosphere. So how much light essentially is received by the planet's atmosphere. So different types of stars will have different ranges, as you can see kind of by this chart here. You've got, teeny stars all the way to giant ones, and you can see how the ranges change. And this one, if I remember right, so this is a runaway greenhouse line, and this is a moist greenhouse, and here's where Earth is. You see it's kind of like right on there. And then Mars is way out here, so it's kind of where it's almost pushing the outer boundaries. So Mars is our outer limit to the habitable zone around our sun. So of course, nothing in science is universally agreed upon. So some dispute the criteria to define inner and outer limits, and that's kind of what the rest of the paper is. It goes back and forth on ideas that have been proposed, and then the authors go, no, we don't like that because of this reason. So one thing I'll focus on is this paper debunks another model that uses cloud cover to justify the habitable zone by stating that if a planet is 100% covered in clouds, then this moves the inner part of the habitable zone to 0.5 astronomical units, which is not realistic. So just for reference, if you don't remember, Earth is 1 astronomical unit from the sun. That's kind of our standard unit of measure. So basically halfway between here and the sun is where they were saying the inner limit is, and that seems very close because Venus is closer to the sun and it's very hot, but it also has a lot of clouds. So if we're going off clouds, I don't know if that's realistic because they have to determine what's in those clouds. So speculating a planet's climate based on gases present and temperatures and relative humidity could also be a way to determine the boundaries. And I think that's what this paper is really pro determining what we could do. Because cloud cover is one thing, but what are those clouds made of? Like how much heat do they absorb and keep in? Because Venus is covered in clouds, but those clouds hold heat. So if there's life on the surface, it's very resilient. So it is best to consider boundaries that are both optimistic and pessimistic, the authors state. So especially because until larger, better telescopes are built, we can't rule too much out. So it's not really a clear answer in the paper. They make their arguments for using a climate model, which I'll get into in a minute, but it's more of a kind of just comparing all the different ideas for habitable zone and stating what they like or don't like. So if we don't rule out too many possibilities right now, we can not eliminate something based on what our notion is right now, and that could change based on scientific evidence later on. Because we don't want to ignore an exoplanet just right now because, well, we know there's no way it could have life. And then, 100 years from now, the data is much better. And they're like, oh my God, these people are idiots. So this paper seems to ultimately determine the use of their climate model, which they describe later on in the paper, along with the use of stellar flux to be the best method of outlining what could be a good habitable zone and what couldn't. So the appendix shows some calculations for possibilities for determining the habitable zone based on temperature and moisture level. I'm not really going to get into that because math, but for those who are more math inclined, it might make more sense. And finally, they propose that a more robust 3D model of climate, so looking at all the different factors, including relative humidity, temperature, cloud cover, gases present, things like that, is the best way to narrow down the habitable zone limits for future work. And I'm going to speculate here that if they do develop such a detailed climate model, it could also be of use when studying our own planet's climate, which is, of course, a very realistic and necessary concern right now because of problems we're having. So here's some of their main sequence stars. You can see these are not as big and bright, and you can see the different zones here. And this so like here's Mars, here's Venus, and here's Earth, kind of right in the middle. And then you go to Mercury's way out here because Mercury's just a rock. And you can see some other exoplanets that they think might be in the same zones based on our own criteria for life, here on Earth and their models. So, here's the appendix with all the math things. Knock yourself out if that's your thing. I really do like these charts that they made here. These are really detailed and I like them a lot. They didn't actually use the term Goldilocks zone in this paper, but that's what I used to call the habitable zone. So that's that paper. Again, I'd be interested to hear your thoughts on should we move the inner boundary out or in, and same with the outer limit. Why should the climate model work or not work? I'd be curious to hear y'all's thoughts. And again, I'll be on Slack if y'all need me for class today. I hope you all liked the discussion, and I'm going to stop the recording now. Thanks.